Soilcast. Boden, Umwelt, Klima.
Have you ever tried pottery? Forming tableware out of a body of clay requires a lot of skill and patience, as I'm sure you're aware of if you have ever tried it yourself. Clay for pottery was very important in ancient cultures to make plates, cups, and vessels to store food and beverages, and is still practiced today. However, clay did not only play an important role for our ancestors, clay is also very important in soils. However, in soil science, the term clay has two different meanings. Let's start with the first meaning. Clay is a measure for the size of soil particles. As we have learned in the last episode, number 4, Texture and Soil Types, clay-sized particles are smaller than 2 micrometers and the smallest particle size in soils. As a reminder, 1 micrometer is 1 millimeter divided by 1,000, so no chance you would ever see a clay particle by eye. The term clay is not only used to refer to the smallest particle size class in soil, but it can also refer to a mineral group within the silicate minerals, the so-called clay minerals. The structure of clay minerals is so fascinating. If you look at a clay mineral under a scanning electron microscope, you can see regular layers that look a bit like flaky pastry or zebra stripes. This is because clay minerals consist of layers. Clay minerals can form in different ways, and I just want to highlight the most important one for the moment. A clay mineral can form out of mica. Mica is a mineral that already has a layered structure, which makes it look sparkly. Where the layers meet at the edge of the mineral, potassium ions are dissolved from the mica mineral by weathering. Maybe you know that potassium is an important plant nutrient, just to highlight again that weathering can release plant nutrients. Now this empty space where the potassium ion has left is open for other cations, and the layer starts to open up with subsequent weathering. Clay minerals can be grouped according to their physicochemical properties. A considerable amount of soil chemistry takes place at interfaces, and this also applies to the interfaces of clay minerals, which is where the layers meet. Water can also enter the interface between the layers of some clay minerals, which makes them expand. You can even see that by eye. Well, you cannot see the uptake of water in the clay mineral interface, but when the clay mineral loses it due to drought. I want you to think of a dried out soil as we see it when we look for images of droughts. On the surface of the soil, there are cracks, right? These cracks form as the water has evaporated from the clay mineral interface, and the clay minerals contract as a result. However, these interfaces do not only bind water. In these interfaces, there is a permanent negative charge to which cations can be bound. You can find exchange cations such as calcium, potassium, and ammonium, which has the chemical formula of NH4+, in these interfaces. Since they are all positively charged, they bind perfectly to this negative charge in the interface. Now, why am I telling you this? Exchange cations such as calcium, potassium, and ammonium are important plant nutrients. However, also pollutants can be stored in these interfaces, which can prevent the pollutants from reaching the groundwater. In soil science, we call the storage capacity of cations cation exchange capacity. Clay minerals are classified according to the number of layers that make up their lattice structure. A clay mineral structure that is made up of an alternation of tetrahedron and octahedron layers is called a 2-layer clay mineral. I will explain more about tetrahedron and octahedron in a minute for all the people who are interested in chemistry. But for now, you just have to know that these are the basic building blocks of clay minerals. I like to think of these 2-layer clay minerals as a burger with a bunch representing the layers. And the exchange cations in between are the meat, veggie patty, salad, or onion, or whatever you like to put in your burger. A clay mineral can also consist of more than just 2 layers. For example, a sequence of tetrahedron, octahedron, tetrahedron, and it is called a 3-layer clay mineral. To make some more food analogies, you can think of these clay minerals as Big Macs, with an extra bun in between. Compared to a regular burger, these clay minerals can store even more meat, salad, and tomatoes, respectively exchange cations and water. Now I want to give a few names and examples for each of these clay minerals. Let's start with our Big Mac-like clay mineral. The most interesting representative of this group is the smectite. These clay minerals can store so much water in their interface that they can swell and shrink a lot. A soil type with high smectite content, such as a vertisol, is challenging to manage because they are not very stable and their water content changes strongly. But hey, they have a high cations exchange capacity and they can store a lot of plant nutrients and pollutants. On the other side of the spectrum is a two-layer clay mineral called kaolinite. This would be our simple burger with just 2 buns and a very poor one. In fact, it's just 2 buns without any meat, salad, or tomatoes. This clay mineral can neither take up exchange cations nor water. How did we get there? In tropical regions where weathering has occurred for a very long time, smectite can transform into kaolinite due to the drop in silicium concentration, which makes smectite unstable. So you can see that clay minerals transform with ongoing weathering. Soils with high kaolinite content, which you can find in tropical regions, are challenging to manage since they have a very low cation exchange capacity and can store only very few plant nutrients. I still owe you an explanation as to why there is a negative charge in between the layers of a clay mineral. Let's take a dive into chemistry. The basic building blocks of a clay mineral are silicon tetrahedra and aluminum hydroxide octahedra. Before I describe the shape of tetrahedra and octahedra to you, I'd rather insert a link in the show notes so that you can see their structure for yourself. In the crystal structure of silicon tetrahedra, the central silicon ion is replaced by an aluminum ion in some places. We call this process isomorphous replacement, and it has something to do with the fact that the aluminum ion fits better into the lattice structure of the tetrahedron. Since we now have replaced a silicon ion, which has an ionic charge of +4, with an aluminum ion, which only has an ionic charge of +3, we are missing one positive charge in the tetrahedra. This is where the negative charge comes from, and as a result, the interfaces of the clay minerals have a permanent negative charge to which cations can be bound. Cool that you're still here after my chemical deep dive. In this episode, we have learned that clay has many more meanings than just the material that is used for pottery. In soil science, clay is a measure for grain size and it represents the smallest particles present in a soil. However, clay represents also a type of minerals, the clay minerals. They consist of layers between which water or exchange cations can be stored. Some of these cations are vital plant nutrients, which is why clay minerals play an important role in soil fertility. I hope you're not too hungry after all my food analogies and that I could at least quench your thirst for clay mineral knowledge. Have a great time until the next episode.
Der Soilcast ist für euch kostenlos und das soll auch so bleiben. Ihr könnt uns dabei helfen. Derzeit unterstützen uns etwa 1% unserer Zuhörerinnen und Zuhörer, zum Beispiel durch eine kleine Überweisung auf das Geschäftskonto oder via PayPal. Wie das genau funktioniert, seht ihr auf soilcast.de unter dem Punkt Unterstützen. Das Geld wird für die digitale Infrastruktur verwendet und darüber hinaus in Technik investiert. Vielen Dank für eure Unterstützung.